In this video, we'll be discussing about the fundamentals of analysis of algorithmic efficiency. We'll be emphasizing on the topics that those are analysis framework, asymptotic notations, and basic efficiency classes. So starting with the analysis framework. In analysis framework, we'll be basically speaking of two topics, that is time efficiency and space efficiency. So in order to discuss the general framework for analyzing the efficiency of algorithms, there are two kinds of efficiency, that is time and space. Time indicates how fast an algorithm would run, and space would tell the extra space acquired by the algorithm to function. So measuring input size and unit for measuring the runtime. So an algorithm's efficiency can be written as function of some parameter n indicating the algorithmic input size. So both time and space efficiency depend on n value. So time can be also explained as number of times the algorithm basic operation is executed, whereas for space it could be told as counting number of extra memory units consumed by the algorithm. So summarizing the analysis framework, it's about time and efficiency and space efficiency. Let's move on to the next topic. We have order of growth here. So order of growth tells in what way the input size is varying. So the efficiency analysis framework ignores multiplicative constants and concentrates on the count's order of growth to within a constant multiple for large sized inputs. So you need to remember this order, that is 1 log n root n or n log n till it goes on till n to the power n factorial. Okay, so here we have the lower bound, average bound, and upper bound part. So when you let's consider one among these each bounds. Let's take log n and n value here and n square here and 2n here. So substituting values in these, we would get this particular graph. So this graph indicates that the values are log n has the least value and n has the higher value, n square has the higher value, and 2n is the highest, which satisfies the given order of growth. Here again we'll be discussing about time complexity and space complexity. So time complexity indicates how fast an algorithm runs. It depends on various factors like compiler used, algorithm used, number of inputs, output, and programming language which is being used. Then we have the space complexity, which tells about the amount of memory required to run the program completely and efficiently. So there are many algorithms for which the running time depends not only on the input but also on the specifications of particular output. So let us consider sequential search here. We'll discuss this further. So an algorithm, the algorithm is sequential search. So initially we are taking an array and we have a key. Okay, so let me take an example of array 3, 2, 1, 4, 5. So this is the array which I have considered, and key value I'll take it as 4. Okay, so 0, 1, 2, 3, 4. Array value here I'm specifying this, taking this as a. So a would be from 0 to n minus 1. N here is 1, 2, 3, 4, 5. 5 values are being entered, right? But then n minus 1, a0 to n minus 1, that is n minus 1. 5 minus 1 is 4. So I have written 4 here, and k value I have specified as 4. So input is array and search key. Output is, if the key is found in this array, then it gives the index position. If key is found, then it returns the index position. If key is not found, then it returns -1. So let's see now. I is equal to 0. Initially taking I value as 0. While I is less than n. 0 is less than n, yes. And a of 0 is 3 here. 3 is equal to 4. No. Initially we check this and get into the loop here. That is I is equal to I plus 1. I value gets updated. 0 plus 1 is 1. So a of 1, I'll move on to a of 1 now. A of 1 I have it as 2. 2 is equal to 4. No. Again I'll increment the value of I. 1 plus 1 is 2. A of 2 is, I get 1. 1 is not equal to 4. Again increment the value. I come to this position. That is 2 plus 1. I have 3. A of 3 is equal to 4 is equal to 4. Now that I have found the value here and I value is less than n here, so I can return the index value, that is 3. 3 is returned as the output. So this was about sequential search algorithm. Now we'll look into the efficiency part. So clearly the running time of this algorithm can be quite different for the same list and array. So if we consider the same list, let me consider worst case first. So in worst case, I have two possibilities, that is algorithm runs the longest time among all possible inputs of size n, no matching element. So if I give key value as 5, then algorithm has to go through all these values, right? So this would be the worst case. Or if I give the key value as 10, which is not present in the array itself, then it will contribute to the worst case efficiency. That is, it has to travel till n whatever the size of algorithm, whatever the size of array is. Suppose here I have taken array with size of 5, but then if you are discussing with array of size 10,000 and you are referring to the last element, here I have the key value, and it has to iterate 9,999 times, right? So it will contribute to the worst case. And if the key value is not found in 10,000th position also, then it is worst case, no? So it has to iterate n number of times. So we can conclude that worst case has n value. Coming to the best case by the definition only we can understand that if the key value is found in the first position itself, if a of 0 is equal to key, then we can return 1, because we can the efficiency would be 1, because the key value is found at the first position itself. You need not iterate to the 10,000 values. Okay, so that was for the best case. Now we have the average case. Average case is combination of best and worst. So like this question, the value is found in the middle, right? So it speaks about average case. So C worst would be n, C best would be 1, and C average would be worst and best, that is n plus 1 by 2. So this is what is mentioned here: C worst, C best, and C average. Here I have the definitions: worst case, best case, and average case efficiency. So this was about the efficiency part. We'll look into the asymptotic notations now. So asymptotic notations is a pretty important topic in exams, and it will be asked for 6 marks or 8 marks also. So the definition says the efficiency analysis framework concentrates on order of growth of n of an algorithm's basic operation count as principal indicator of algorithm's efficiency. So to compare and rank such order of growth, we make use of asymptotic notations. So asymptotic notations tells us the study of how value of function varies for large number of n, where n is size of input. Here we ignore the small constant values. So asymptotic notations are used to compare order of growth. Here we have 3 notations: big O that falls under the upper bound, then big omega lower bound, and big theta, which is a verge bound of a function. So we'll start with the big O notation first. So big O notation, the definition goes as: the function f of n is said to be big O notation of g of n if and only if there exists a positive constant c and some non-negative integer n naught such that it follows the below equation. F of n is less than or equal to c into g of n for all n greater than n naught being a non-negative integer here and c being a constant. So defining this particular equation in graph, so f of n is here, so f of n should always be less than c into g of n. That's what big O notation says. F of n belongs to big O of g of n if this condition is satisfied. So to prove this, f of n is equal to order of g of n, take c to be sum of positive coefficient of function of n. So we'll consider the problems now. F of n is equal to 2n plus 3. We need to prove that it follows big O notation of n. Okay, so to prove f of n is equal to order of g of n, we can take c to be sum of positive coefficient of f of n. So here they have told us that this function should follow big O notation with n value. So here I can write, firstly I'll write f of n value as it is. So here I'll write 2n plus 3, and on this side I have to somehow make it of this form, that is less than equal to. So 2n plus 3 less than equal to what can come this side, such that order of n should be satisfied. So here I'll write 10n. Now I'll take n value as 4. Okay, 4 to the 8, 9, 10, 11. 11 will come here, and on this side I have 10 into 4, 40. So I can say by taking 10n on this side, I am satisfying this condition, right? So I'll write the condition here again, greater than c into g of n. Now what is c and what is g of n value here? C value I can take as 10 and g of n value I can take as n. So by taking this, I can write this particular equation, f of n obeys g of n. The c I'll neglect, okay. Falls under order of n. This is satisfied. Okay. Now let's look into the second question. F of n is equal to n square plus n. I need to prove that it obeys order of n cube. Okay. So in order to prove order of n cube, I'll write f of n value here first. 2n plus 3 greater than value should be there. N square plus n. N square plus n is there. Here I'll put 2n square plus 3n or 3n square I'll write. Okay. I have to fill something here such that this has to be less than this. Okay. So I'll take n value as 1 here. So I get 2 plus 1, 2 into 1, 2 plus 3 is 5 on this side, and on this side I have 1 and 1 here. So here again 5. Here the condition says that f of n should be less than or equal to c of g of n. So 5 is equal to 5. That is, this condition is satisfied. So I can write c value here as 5 and g of n value here as n square, because 5n square I got here, right? This is c and this is n square. So I can write order of n square, big O of n square. Now I'll look into the last question. F of n is equal to 100 n plus 5. And here I need to prove it is order of n square. Okay, to prove order of n square, I'll write 100n plus 5 here first. And on this side it has to be greater. So I'll write 100n square. So I'll take n value as 2 here. So 100 into 2, 200, 200 plus 5, 205 should be less than 100 into 2 square. 2 square is 4. 4 into 100 is 400. So 205 is less than 400. This condition is satisfied. So I can write c into g of n here. So here c value is 100, that is the constant, and g of n value is n square. So this condition is satisfied, order of n square. So in the exam, if they ask for big O notations only, it would be from these questions only, because I've taken this from previous year question papers and referred the textbook as well. Let's move on to the next topic, that is omega notation. We have omega notation next. So omega notation, the function omega notation comes under the lower bound, okay, big O, big omega. Okay, the function f of n is equal to omega of g of n is said to be big omega notation if and only if there exists a positive constant c and some non-negative integer n naught, such that f of n is greater than or equal to c into g of n for all value n greater than n naught. So previously in big O it was less than or equal to, here it is greater than or equal to. Okay, which says that if f of n is there, the c into g of n value should be less than that or equal to that. Okay, and it ranges from n naught value itself. Let's consider this example. Here they are given f of n is equal to 2n plus 3. We need to prove omega of n. So firstly I'll write the f of n value as it is, 2n plus 3. Here I should do something in order to get greater than equal to 2n plus 3, and here it is to be proved for order of n. Okay, so here I'll write 2n plus 3 itself. Let me write the same, okay, or let me remove the constant one. Plus 3 I'll remove it off, I'll keep this. Now I'll take n value as 1. Okay, so if I take n value as 1, 2n plus 3, 2 into 1 is 2, 2 plus 3 is 5, and on this side I have 2 into 1 is 2. So 5 is greater than 2, which says that this condition is satisfied. Yes. Now in 2n, if I write c into g of n, c constant value is 2 and g of n is n. So I have proved that it belongs to omega, big omega of n. Coming to this part, this question, I have 2n square plus 3n plus 4. I have to prove it as omega of n square. Let me write the f of n value as it is, 2n square plus 3n plus 4. This has to be greater than or equal to whatever on the n square side here. So I'll write 2n square and I'll remove all this, okay, neglect all this. Now I'll take n value as 1. Let me see, 2 into n square, 1 square, 2 plus 3 plus 4, 4 plus 3, 9. Here I have 9 greater than 2 into n square. N square is 1, 2 into 1 is 2. This condition is satisfied. Now I have 2n square here, which is equal to c into g of n on the LHS side. Now if I write constant value, that is 2, and g of n value as n square. So I have proved that this particular function obeys omega of n square. Now if I look into this particular question, n cube plus 4n square belongs to omega of n square. So I'll write n cube plus 4n square should be greater than or equal to, this has to be greater than or equal, okay, and n square is asked here. So I'll write 4n square on this side. I'll neglect n cube, okay. Now I'll take n value as 1. So 1 plus 4 greater than 4. 5 is greater than 4. Again 4n square is equal to c into g of n. Now if I write c value as 4 and g of n is n square. So it is clearly understood that it belongs to omega of n square. The asymptotic notation here is omega of n square. So this was about omega notation. Let's move on to the theta notation now. So theta notation is the function f of n is equal to theta in theta of g of n if and only if there exists a positive constant here, two constants, because it comes under the verge bound function. So c1 and c2, two positive constants should be there such that it follows this particular condition. The condition says that f of n should be between c1 and c2 values. So f of n should be among c1 and c2 values. We'll understand this with an example now. So f of n is equal to 2n plus 3. So that's the same example, 2n plus 3 and theta of n. So I'll write 2n plus 3 here. So firstly it has to be greater than c1 of n and c2 of n, right? Theta of n they have asked. So c1 of n, c2 of n, this condition should be satisfied. In order to satisfy this condition, I'll take c1 of n as 2n plus 3 plus n, okay. And in order to satisfy this condition, this c2 condition, I'll take just 2n. Now let me fill values. N value, let me take it as 1, okay. So 2 plus 3 plus 1, 6 I have this side, and on this side I have 2 plus 3, 5, and on this side I have 2. So 6 is greater than 5 and 5 is greater than 2. So this is c1 part and this is for the c2 part. So I can say constant c1 is 2n plus n is 3n. 3n plus 3. So 3n plus 3. So if I take 3 common outside, I get n plus 1, right? C1 is 3 and g of n is, I can write it as 2n, 3n plus 3, okay. And on this side I have 2n, that comes under C2. So we can say that it obeys theta of n condition. Then we have n square plus 5n plus 7 here. So for this I can write n square plus 5n plus 7 in the middle. I'll write this side c1 value, I'll write it as n square plus 5n square plus 7. I'll neglect it. Here I'll neglect all this and I'll keep 5n itself. So if I take n value as 1, here I get 1 plus 5, that is 6, greater than, here I have okay, I'll take n value as 2 here, okay. So if I take n value as 2, it'll work out properly. So 2 square is 4, 4 plus 5 into 4 is 20. So here I have 24. This side I have 4 plus 5 2s are 10 plus 7, 17, 21. And on this side I have 5 2s are 10. So 24 is greater than 21 and 21 is greater than 10. So C1 of n is this and C2 of n is this. So this I can say that it belongs to theta of n square. Okay, so this was about the second question. Explaining the third question, I have f of n value as half into n minus 1. So for big O, so the first part, it is f of n should be less than C2 of g of n, right? This is only the condition. So I can write that half into n minus 1 can be written as, can be equal to n square, multiply this n square minus n by 2. Now if I take n value as 1, so if I take n value as 1 minus 1, 0, here I'll get 0, here again 0, 0 is equal to 0, satisfied. So the first part is satisfied. Now to the second part, f of n greater than c1 of g of n, half n square minus n, half into n square minus n I have, greater than, here I'll write, here again I'll write the same thing, half n square minus n. Now I'll take n value as 1, okay, so I get n square by 2 minus n by 2 greater than or equal to n square by 2 minus n. Now if I take n value as 1, half minus half, half minus 1. So half minus half is 0, 0 is greater than, here if I take n value as 1, 1 by 2 minus 1 is 1 by 2. So 0 is greater than 1 by 2. So again, C2 of g of n is satisfied and C1 of g of n is satisfied. When these two conditions are satisfied, you can say that it belongs to theta of n square. So this was about theta notation. So I have tried to cover all the important questions which are asked in the previous year paper and internals or the internals. Let's move on to the theorem. This is a pretty important theorem which is always asked in the exam. It could be asked for 7 marks or 6 marks. So let's start understanding this theorem. So if T1 of n belongs to order of G1 of n and T2 of n belongs to big O of G2 of n, then T1 of n plus T2 of n should belong to big O of max of G1 and G2. Okay, so we are considering 4 arbitrary real numbers A1, A2, B1 and B2. Okay, so if A1 is less than or equal to B1 and A2 is less than or equal to B2, then A1 plus A2 should be less than or equal to 2 times max of B1 comma B2. Yes, this is understood. Here we have, since T1 belongs to big O of G of n. Big O of G of n means it should satisfy this condition, right? And for C2 also it should satisfy this condition, right? For T2 also it should satisfy this condition. These two are understood by the big O notation definition. So let us denote constant C3 as maximum of C1 and C2, and constant n, consider n as greater than or equal to max of n1 and n2. So using inequalities and adding these inequalities, we can get T1 plus T2, T1 of n and T2 of n can be summed up as C1 into G1 of n plus C2 into G2 of n, which comprises to C3 into G1 of n and C3 into G2 of n. Because here I have specified, right, C3 is max. So further I'll write it, considering C1 and C2, I'll take it as C3 into G1 of n plus G2 of n. Now I'll take C3 here, and G1 of n, G2 of n can be written as 2 times max of G1 of n and G2 of n. So hence I can write T1 of n plus T2 of n belongs to big O of max of G1 of n and G2 of n, and maximum of n1 and n2, because n1 is considered for the first one and n2 is considered for the second one, right? For this it is n1 and for this it is n2. So maximum of n1 and n2 is considered. So this is about the theorem part. Here if we take an example, half of n into n minus 1. So the first part, if we go, it is n square, and if we take just the n minus 1, second part, it is order of n. By taking these two, we are considering, we are applying this theorem, can get order of big O of max of n square and n. So whichever is maximum would be selected, that is n square. So order of n square is the order of growth which is considered for the sorting algorithm. So this was about the theorem. This is a must question. One has to understand this theorem properly or just mug it up properly, because it is definitely asked in the exam. Next we have using limits for computing order of growth. So when we have two equations, okay, so how will we compare the order of growth? And that will be discussed here. So if it is of the form limit n derives infinity, t of n by g of n, we need to take the two limits and write it in this form. And if it equates to 0, then t of n has smaller order of growth than g of n. And if c is greater than 0, the constant is greater than 0, then they have same order of growth. And if it is theta, if it is infinity, then t of n has greater order of growth than g of n. In order to solve such problems, we'll be using two major rules. That is, one is the L'Hopital rule and other one is the Stilling's formula. I'll explain this while solving the problem. So first we have compare order of growths by considering the limits half n into n minus 1 whole square and n square. This is the first question which I've got. So let's solve this question. Let me write it in this formula, limit formula. Limit n derives infinity. On the above I'll write t of n, and here I'll write g of n. That is, t of n is half n into n minus 1. Here square is not there, n into n minus 1, and on this side I have n square. So taking this half outside, I'll write half outside. Here I have n square minus n, multiply this n inside rule. I can solve it directly, right? Half outside, limit n derives infinity, n square minus n, and here I have n square. Let me take n square outside, n square out. Here I have 1 minus, if I take n square out here, I'll get 1 by n here. N square I can cut. I have 1 minus 1 by n left. So I can write half, because 1 minus 1 by n, let's take it as some constant part. Okay, here I have half into something. Okay, so it is positive only. So when c is greater than 0, then I can say that t of n and g of n has same order of growth. So this was about the first question. Second, I have log to the base 2 and under root n. So in order to solve this, I'll write the limits initially. N derives infinity, under root n. So whenever I have under root n in the below, whenever I have under root n at the below part, I can use L'Hopital rule. Okay. For this question, I'll be using L'Hopital rule. So that says limit of n derives infinity, log to the base 2 by under root n. So here I can write this as limit of n derives infinity. This I can write it as log base 2 e power 1 by n, and here I can write under root n is there, no? So I can write it as 1 by 2 root n, applying the formula here, t dash and here g of n. Okay, and here g dash n. So here I get 2, let's take 2 outside, 2 into log e base 2, and here I can write limit n derives infinity under root n, which would be, it will go up under root n by n here. So further writing 2 into log e to the base 2 under root infinity by infinity, because I have applied the limits here. So if I apply the limits, log of infinity by infinity, it will turn out to 0. No, this entire thing would result to 0. If this entire thing results to 0, then t of n has smaller order of growth than g of n. So t of n has smaller order of growth than g of n. Let me move on to the third question, that is n factorial and 2 power n. I'll write limit of n derives infinity n factorial by 2 power n. So further writing this, I'll be applying the third equation, that is Stilling's formula. Whenever I have n factorial, it could be written to the form under root 2 pi n, n by e to the power n for large values of n. Okay, so let me write the value here, n by, so this is the formula, right, n factorial by 2n. So this I can write it as limit of n derives infinity under root 2 pi n n by e power n by 2 into n, 2 to power n. Further solving this limit of n derives infinity, 2 pi n, let's take it outside. Here I have n by e by n by 2 power n. Solving this further, I can write n by 2n e n. This e, take it down, okay. Further I can write under root n into n by n, and because 2 pi you take outside, here I'll write it again. Here I'll write 2 pi under root, I'll be left with under root n and n by n, and below I have 2n into e power n, which can be further written as 2 pi, I'll take it as 1 by 2, this root as 1 by 2, and here I have limit of n derives infinity. This could be written as n 1 by 2 into n into n. So this I can add, the above part I can add, right, powers I can add 2n plus 1 by 2, and on the bottom I can club 2e, so 2e power n, common n value. So if I substitute infinity here, it'll go to infinity itself. So I can say that t of n has larger order of growth than g of n. So this was about comparing order of growths. So these questions are pretty important, and regarding this topic only these 3 questions would be asked in the exam or in the internals also. So I hope you have understood these topics. If you have any doubt, do let me know in the comments and subscribe to my channel. Thank you.